Yeah, I mean, Harrison, you're right. You're probably right in most instances, but probably, you always want to check that. Okay, we're recording. We're live. Let me get the presentation full screen. Okay, welcome back to Steel Design. We are done with bolts, so we are in the land of welding today. Just so everybody's aware for the schedule, so number one, no homework assigned today because today is just going to be, movie time about welds. One thing I did want to mention though, and I'm perfectly fine to open it up to questions, but I think there's still like a little bit of confusion about the maybe block shear. And I mean, we're past block shear, and I'm not gonna put it on any other exams, but I want to make sure that you understand it because we've been looking at the exam corrections, and it seems like there's still like some confusion on how block shear works because some of the areas on the exam corrections are still like off. So I want to show you something. Let me stop this share here. Where's my inventor? Okay, so this is inventor. So the exam problem that you were correcting looked something like this. It was a channel bolted through the web. Okay, so when you look at the shear path, if you will, or the block shear path, it looks something like this. Okay. So there's two shear paths. There's one up here and there's one down here, okay? So to make sure that everybody's clear on that, when you look at your areas, let me stop this share, go back to, this. So, I don't remember the specifics of what the problem looked like, but actually, I'll go ahead and pull it up just to kind of make sure that we're all kind of talking about the same thing. So here's what the channel looked like. It was like this, it was like that, and it was like this. That's what it looked like. The failure block looks like this, okay? That's what the failure block looks like, okay? A lot of you, I think, were doing that, or like doing this. Like that's wrong. That's not right, okay? Because then you'd be ripping through all of that material at the bottom, okay? So, when you're doing AGV, this dimension was 8 inches. AGV is 2 times 8 times TW. And then ANV is AGV minus 5 bolt holes, okay? Not yet, because we haven't finished grading them yet. They will, but not yet. But the point I'm making here is that this is in shear, but also that as well. So there's 2 shear paths. And as for the holes, it's 1, 2, 3, 4, and then 5 because you get a half on each end. The ANT, or the for tension, this dimension was like 2.5. So AGT is 2.5 times TW, and ANT is AGT minus 1 hole. And then all of these will give you the capacity for 1 channel. Okay? One channel. Once you get an RN, you got to take that RN and double it because there's 2 channels. Then you multiply it by phi, and then set that equal to 1.2 dead plus 1.6 live and solve for live. And so the answer, I think, I don't remember, let me see. The answer ended up being something like 107 kips. But I'm more interested to make sure that you understand, because it seemed like there were still some folks that didn't get it. Does that make sense? Does anybody have any questions on that? I mean, I'm not going to ask you on an exam. We're not talking about exams. I just want to make sure you get it. All right. I got one person that said bingo, so I'm going to go with it. But again, the big point I want to make sure that gets across is if there's something you don't understand, like, let me know, because again, I'm sitting Marco Polo. I'm sitting here talking to a little box on my desk. I don't, beyond chat, I don't know if somebody gets something or not. So let me know if something doesn't make sense or whatnot. Okay. So we're going to talk about welding today. Welding is a little different than bolting, just because of the skill set that's required. I'm sure that there's things that you'll learn in the field that it was about block shear, just whether or not you understood block shear about the exam corrections. But we can talk about that later. Today I want to focus on welds. When it comes to welding, we could be installing bolts in structures like today. You could get a little bit of training on the equipment, and there's not an inherent learned skill that it comes with bolts. I mean, granted, you'll learn things in the field, and there's always tips that you can learn, tips and tricks, but it's not like welding. Welding is almost an art form. It takes years to master the skill. There's a reason why trained and certified welders do very well in terms of their salary, because it's not the easiest thing in the world to do. It takes skill. I'm curious if there's anybody in the class that has ever welded anything before. I have. I'm okay at it. Like, I can get piece of metal A to join to piece of metal B. But every now and then you'll find a couple bubbles in my welds. I won't lie. Has anybody in here welded? And if so, what type of welding have you done? Has it been stick welding, MIG welding? Okay, there's a Dr. Bryce avatar and a Dr. Mike avatar. Now there's a competition. So stick and MIG. I personally prefer MIG weld. I think I'm better at MIG welding than I am stick welding. But that's just me. I think MIG welding's easier, but I know a lot of certified welders, folks that do welding for a career, at least a lot of the ones that I've spoken to, think that stick welding's easier. But that's me. I as Trevor said, he likes stick because he can make it pretty. I do have a hard time making MIG welds look good. And Mr. Enoch said, I don't know the difference between the different kinds of welding. We are going to talk about that today. So let's talk about the different types of welding, because Mr. Enoch is stealing my thunder a little bit. Well, he hadn't stolen my thunder, because I'm going to show that. But he's definitely prescient and got a little bit of precognition there. We're going to start by talking about the different types of welding that we use. And I'm primarily focusing on the type of welds that we use in... you might be on something there. There are four main types of welding that we use in structural applications. So some of you who've done maybe some mechanical welding, you might have experience with TIG welding and stuff like that. We don't do that in large-scale structural applications. We mainly use four different types of processes, and these are the technical scientific terms for the processes. We have shielded metal arc welding, we have gas metal arc welding, we have flux core arc welding, and submerged arc welding. And each of those have particular applications and reasons why we would use them and reasons why we wouldn't. And so I want to look at each method and its advantages and disadvantages. So let's start off with shielded metal arc welding. So shielded metal arc welding, you've probably referred to that as heard of that as stick welding. Okay, so I'm gonna, if you want, you can hop back and forth between my camera. I'm gonna pull my camera up. So this is a box of weld electrodes here, and I'm gonna show you something about these electrodes either. But this is from Lincoln Electric, and so when you open that, you can see this is what a weld electrode looks like. Kind of looks like a little stick, and that's why we call it stick welding. And so basically what way it works is, if you look here on the slide, you'll see that the welder, here I'll switch back there, the welder has sort of, it looks like a jumper cable that grips the electrode on one end. You can see here's the electrode, and you can see that it has an exposed end that the welder would grip onto. And then there's another connection on the workpiece, the plate or whatever, you know, section that you're welding. And so once you touch the electrode to the workpiece, you complete the electric circuit, and then energy starts to flow, and you start to melt the tip of this this electrode. Now, if you look at the electrode has, you know, there's this exposed end, but you can also see this sort of, you know, granular coating on it. It's this like gritty stuff that coats the electrode. And this coating, once you complete that circuit and you start to melt the electrode, this coating, starts to, you know, react as well. And it forms this gas shield right there at the connection point between the workpiece and the electrode. So whenever you look at a weld being placed, you know, not only do you see sparks, but you'll see this gas shield being formed. What that gas shield does is it prevents impurities from the atmosphere getting into the weld. One of the big enemies of welds in terms of their performance is hydrogen. You don't want hydrogen to get into a weld because that can lead to very brittle welds, which is why, you know, this shield is present. And so that's what stick welding is. Stick welding, sort of one of the advantages of stick welding is that you tend to get deeper penetrative welds with stick welding as opposed to MIG welding. But I guess, you know, one of the disadvantages is, you know, you've got this electrode. As you're welding, you are, you know, depleting this consumable. This consumable is being melted, and then after time, you're going to have to get rid of this and go to a new one. And so whenever you buy a box of electrodes, there are just a bunch of these in here. And so once you get rid of them, you have to keep using them over and over again. So stick welds are for, you know, deeper penetrative welds, or essentially welds where you need, you know, that bump in capacity. Now, the other, you know, very common type of weld is what's called, let me get my pen here. The other common type of weld is a gas metal arc weld, which is probably, you all are familiar with, is MIG weld. Okay. Now, MIG welding, first off, the mechanics of depositing the weld are entirely different. So with stick welding, you have these, you know, discrete electrodes that, you know, you're using, and then once you're done with it, you move on to the next one. You keep replacing your electrode. With MIG welding, it's a little different. So MIG welding, you're going to have like I guess a box is the best way of putting it. There's a box that contains all of the, you know, electrical equipment, you know, that provides the voltage and the energy into the system. Yeah, that's a good question. That's a very good question. I got this. I just pulled this off the internet, and I liked the image because it showed the MIG welding being applied to a structural application. But yeah, the fact that this guy has no eye protection is a massive no-no in OSHA land, because you brought up a secondary point I was going to bring up, and that's a great point. So MIG welding, there is a continuous wire that is being fed through this gun that the welder is holding here. So this box, not only does it contain the electrical equipment that provides all the energy and whatnot, it contains a spool of electrodes. And so the spool will look like a drum about this big around, and it looks like little copper wire is kind of what it looks like. It looks like this copper colored wire that gets fed through this, you know, tube or this hose into this welding gun. And so the nice thing about MIG welding is you don't have to keep replacing the electrode. You just hit the little trigger on the gun, and the weld electrode spins out. And then on the box, you know, you can adjust the speed at which the electrode is deposited. You can adjust the voltage. You know, the higher the voltage, the more energy. So if you want a deeper weld or you have a thicker plate, you know, you need to bump up the voltage. In addition to depositing the electrode, the consumable, there's also a connection to a tank of gas. So if you ever see MIG welding, a shop MIG welder, not only do you find the wheel of consumable electrode, there's also a big old tank of gas, and that tank of gas is an inert gas. When you hit the trigger, not only are you depositing the electrode, but you're depositing this gas shield as well, and it's doing the same thing that the this granular coating on the stick weld is doing. It's shielding the weld from that that embrittlement. And you know, Trevor hit the nail on the head. Whenever you're dealing with welds, welds are, I don't want to say dangerous to deposit, but you do have to take certain safety precautions. For instance, if you look at the welder, not only is the welder providing a, you know, he has the helmet on that's, you know, shielding his eyes from the ultraviolet, but he's also got gloves that go past his wrists. He's wearing, you know, long sleeve shirts because that light can kind of give you a sunburn. In fact, you know, whenever the eclipse went back, when we had that, you know, massive solar eclipse, you know, there was folks putting welding helmets on instead of those little visors because it was blocking the ultraviolet. Not sure if that was the safest thing to do, but it's kind of funny. Unrelated to welding, but on the picture to the right, what purpose do those plates sitting perpendicular to the web? That's a great question. So what are these plates? That's a great question. Those plates that the welder is welding to this. So if this is a beam, if this is a flexural element, so think like shear and moment diagrams, those plates would stiffen the girder's resistance to shear, so that they increase the shear resistance. The other thing that they can serve to do is to connect cross frames. So for instance, if you look at this element here in the back, you can see that there's stiffener elements every so often, and so there might be like a cross frame that connects every so often. So for instance, if you have you know, here's your girder, you might have a plate here because there's a cross frame, and then you might have a plate here and there's another cross frame, and those cross frames prevent the girder or you know, increase the girder's stiffness under bending, because in bending where the top's in compression, it wants to buckle, and that'll be something we talk about in around April. We spend a lot of time talking about bracing and LB and all sorts of that stuff, so we will sort of indirectly cover that later in the semester as well. And if I have time, I'll talk about shear resistance. One of the things about steel design, particularly steel in buildings, is that shear on beams tends to not be a big deal. It can for plate girders and bridges, but for beams and buildings tends to not be the biggest concern in the world, and that'll be more clear as we progress throughout the semester. All right, any other questions? All right, so a couple other methods. So those are really sort of the two big methods, is stick welding and MIG welding. There's also sort of a couple other offshoots. One of them is called flux cord arc welding. Flux cord arc welding is very similar to MIG welding. In fact, you know, if you have sort of maybe a welder in your garage or something, you probably use flux cord if it's a small welder. The difference is that the electrode, instead of using like a tank of gas shield, the electrode contains a flux, which also you know, generates that gas shield, so you don't need an extra tank. And the nice thing about that is because you're not using a tank of gas that you're sort of shooting on the weld as you deposit it, flux cord works really well if you're gonna weld outside. You know, because if you're welding outside and it's windy, all that gas shield is gonna get blown away. So because the weld contains the flux, you don't really need to worry about that. So it's kind of an advantage there. The other process is what's called submerged arc welding. The submerged arc welding is really only used when you have like a really long continuous weld. So like if you're welding like a top flange to a web and a plate girder, you might do this because that weld's going to be, you know, like 60 foot long or 120 foot long. And so what it looks like is this is the method that's sort of done by a robot. This isn't really done by a person. Basically what you'll find is a weld being deposited in one continuous bead, but the weld is actually submerged under this granular flux. It kind of looks like kitty litter. And so one of the things, you know, when you look at submerged arc welding, because the weld is being done under that flux, you really don't see as much of that bright light that you would get from you know, the UV from, you know, stick or MIG welding. But you know, just you just to again qualify, this is a process that's done more for long continuous welds. You're not going to do this for welding like a clip angle to a beam, where the weld's only that long. You're just going to break out a stick or a MIG and do that yourself. Any questions about this? I'm just curious, because I know for some of you, you might know this stuff, and for some of you, this might be the first time you've ever seen it. So, okay. It's fun. I mean, like the first time that you weld, it's a lot of fun, but it's definitely something that it is a learned skill. It's not something that you just pick up and do one day. It takes practice, but it's worth trying out. Yeah, know how much welders charge. Yeah, that's true. They charge a fair amount. Now, those are the welding procedures, like the equipment that we use to deposit welds in structural applications. But what about the types of welds themselves? Well, there are various types of welds that we use in structural engineering. I want to talk a little bit about them. First off, I think that I would be remiss if I didn't discuss the tack weld, which is, I think every single welding operation involves a tack weld. Now, to be clear, tack welds are not something that structural engineers design, because their purpose is not to resist load. Their purpose is not to support, a structure. Their purpose is only for fabrication. So the idea is, okay, I have this weld that I'm going to place. I'm going to join piece A to piece B. So what I'll do is I'll get the piece sort of where I want it. I'll clamp it down, and I'll hit it with a weld real quick, just like a little quick, 1 second deposit, just and then done. The purpose is just to sort of get it in place, so tack it in place. That's why we call it a tack weld. And so if, once you finish your tack weld, you go and you measure it again to make sure, okay, is it in the right spot? Do I need to move it? Because if it isn't, if you have to adjust it, you can grind that weld off and reposition. So you always tack it before you deposit your real weld. And as for the real welds, there's a series of welds that we use, but by and large, the most common type of weld that we use in structural engineering applications is the fillet weld. The fillet weld is just probably what you're thinking of when you think of a weld. Piece A, piece B, place a bead of weld along those two adjacent members. That is the most common type of weld that we use in structural engineering. I'd say, gosh, like 80 to 90% of the welds that we use are fillet welds. And so that's all we're going to focus on in here. The others, it's not terribly difficult for design, because you end up placing the weld such that you develop the capacity of the base metal, and so it's really just more of a fabrication issue than it is a design one. The other types of welds that we deposit in structural engineering are groove welds. And so a groove weld is when you basically have a groove cut between two plates and you're just filling it with weld metal. And so this is really more used to splice plates together. And again, you're welding that so you develop the capacity of the base metal, so that usually the weld doesn't govern in those instances. And then there's also plug welds or slot welds. They're not as common, but basically you have a hole drilled in a plate and you just fill it with weld metal. They can be used to transmit shear or prevent buckling, but again, they're not very common in most applications. They're admittedly pretty rare. So here's some images of what some of these welds look like. This is kind of what a tack weld would look like. Again, you're just hitting it with that short weld just to make sure you got the piece lined up and where you want it. But that over there on the right, that's a fillet weld. That is by and large, the most common type of weld that we use in structural engineering applications, and what we're going to be focusing on for the purposes of design. Just so you're aware of what some of these other welds look like, this is what a groove weld would look like. We tend to spec out groove welds with in two different classes, either a CJP weld or a PJP weld, and so that's either complete joint penetration or partial joint penetration. But again, that's basically filling that with weld metal so that you develop the capacity of the plate, and it's mostly used for splicing. Plug welds, so again, there's a hole drilled in that plate and you just fill it with weld metal, but again, pretty rare. Okay. Joints, we talked a little bit about this, in bolted connection land. We mostly dealt with lap joints, where we had a plate lapped onto another plate and then we, bolted between them. As for welds, there's a couple different ways that we could go about this. So we have lap joints, we have T joints. So, for instance, if you're looking at a plate girder, so you've got the web and you're trying to weld it, say, to the bottom flange, that would be a T-joint. And so you might place fillet weld, like here or here, something like that. Maybe for a lap joint, you're welding that or that. Butt joints, that's going to be, sort of your groove weld, your CJP or PJP weld. Corner welds and edge welds, not as rare, but you could, place weld here or maybe fill in, weld there. Do pipe welds have different naming schemes? You mean like joining pipe A to pipe B? Is that what you're talking about? Well, you're still placing the same type of weld. You might classify it as a groove weld, but you're still doing the same thing. One thing to keep in mind is that we don't do that very commonly in structural engineering applications, because most of the time pipes are used. They're used for column sections, and because the way that we erect them, we can splice those with field splices, and so we usually don't really need to do that. Now, that's not to say that they don't weld pipes together, but it's not as common for structural engineering. It might be for water systems or something like that, but we don't really use it all that much in that fashion. It's not to say we don't do it, just it's kind of rare. Yeah, and what you're talking about there is really more in mechanical land, or it's not really in civil land. It's not to say it doesn't happen, but how would you classify it? I classify that probably as a groove weld, because you've got a groove in it and you're just filling it. Get it, though, it depends. Okay, this is good stuff. Any other questions? How can a weld weaken? Welds on desk look like they've been sheared off. Could have been. Well, there's a number of reasons for that. You could have a weld that was just didn't have much weld penetration. It didn't. It was placed poorly. It was brittle. So there's the quality of the weld. That's the first reason a weld can fail. Welds, by their nature, you are introducing a flaw into the material when you weld something. So that flaw can be amplified by fatigue. If you have something that's that's loaded and unloaded, much like the tab of a soda can, the weld can fail by developing cracks. So that's another reason that welds can fail. Beyond that, they could just fail just under load application. But we could probably be defining limit states all day for different reasons weld fails. It also depends on just the geometry, stress concentrations. It's we could go on from there. The other thing I do want to mention, this doesn't really matter for structural design purposes, but it's something that I think you just need to be aware of as an engineer, is the welding position. And so the welding position, just if I'm the welder, that's whether or not I'm welding it flat, or if I'm welding it like horizontally, or if I'm welding it, overhead, or if it's a vertical weld. I don't know if anybody in here has done any welding. One of the things that they'll tell you is if you look at this chart, the difficulty increases as you go down, right? So the easiest weld to place is sort of just where it's here and the piece is laying flat and you're just depositing it like that. Whereas if you place, like an overhead weld, you're literally placing it like this. You've got molten metal going like that. It's kind of difficult to get that weld done correctly. I've placed a couple vertical welds before, and they were tough. It was not easy. I got it to work, but it didn't look pretty. I'll just say that. So it's definitely something to. When grinding a weld, does it weaken? It depends. And I'll be able to answer that a little more clearly here in a bit. Bear with me. I'll be able to answer that more clearly in a bit. Okay. And what I'm getting at is sort of Benjamin's question. But I'm going to answer that question specifically about fillet welds. Okay, the final thing I want to talk about before we start getting into the math are welding symbols. So whenever you're producing engineering drawings, we have a series of symbols that we utilize to indicate what's going on with the weld. So for instance, if I have a plate and I have another plate, let's say this, well, that shouldn't really matter for what we're talking about. And if you're talking about specifically maybe about like the steel bridge competition, that won't matter. But just bear with me. You'll see what I'm talking about here in a second. Okay, so let's say you have a plate like this and you're depositing a fillet weld, something like that. And let's say that weld is 1/4 of an inch, okay, which is a somewhat common weld size. And let's say that the weld is ultimately going to be, 6 inches long, okay? So what you're going to do is you're going to indicate this with a weld symbol. You're not going to just dimension it out like this. And so the way that you would indicate this particular weld is you'd have an arrow pointing to it, and what you would do is you'd use the fillet weld symbol. You put it here on the bottom since it's on the arrow side, and this is going to be 1/4 and 6 inches long. And don't worry, I have a slide here in a bit that indicates that shows you all the symbols that you need to know. If you look at weld drawings for like complex machining equipment, they look crazy. Just all the different symbols and diagrams and whatnot. It can be very tough to discern. And so I'm not going to make you go through and try and memorize all that. Believe me, I'm not going to do that, because there's all sorts of different there's all sorts of like wild stuff that you can see. So like for instance, if I put a little flag right there, that means it's going to be done in the field as opposed to being done in the shop. If there was a circle, that would mean you'd weld all around. I mean, they can get kind of nuts. All I want you to know is this right here. This is all I care about. So first off, I've got 2 images here. Okay, the difference between the two is one has a weld on one side and one has a weld on both sides. And you can see what's going on with the triangles. The triangle is the symbol for the fillet weld. So if I put the symbol on the bottom, these are like accepted symbols. This is like the way that you do it. For a fillet weld, if you put the symbol on the bottom of the line, that means it's on the arrow side. So you can see how the arrow is pointing here. And so the weld is on that side. So that's why we put it there. But over here, because it's on both sides, we put the triangle on not just below the line, but above the line. They're both 1/4 inch welds. One of them is 6 inches long. One of them is 8 inches long. That's all I care about for symbols. I mean, I don't really get too marred up in you memorizing weld symbols. We've got bigger things to discuss. I'm more interested that you understand how to compute the capacity of a weld and how to detail and size out a weld. That's what I'm more interested in. Any questions before we talk about how to compute capacity? Because again, like if bolted connection, if you understood bolted connections, I think welded connections are even easier to do from a math perspective. They're really not hard. But I just want to make sure that you understand sort of the ideas. Okay. All right. Let's talk about the capacity of a fillet weld. Okay, so I want to talk about fillet welds, and I specifically want to talk about a dimension called the effective throat. So over here on this image on the bottom, looking at this, okay, this is sort of a schematic of a weld, like an actual deposited weld. And one of the things that you'll see is, when we're depositing a weld, we're depositing this bead of weld joining point A or part A to part B. And so in real life, here's the plate. And in real life, the weld kind of looks something like that. It's got this rounded bead, sort of shape to it. And what we do in civil engineering, structural engineering, and even mechanical engineering, they do the same thing, is we assume, just for geometry's sake, to keep things simple, we assume the weld looks like this, just like a right triangle. And a right triangle, maybe where this is A, and this is A. So like a 45, 45, 90 triangle. So to go back to like the question Mr. Thews asked, he said, what about grinding? I said, well, as long as you don't grind into that triangular region, you want to maintain that geometry. Like if you ground this so far that, you know, you were grinding into this area, that would not be good, right? So that would be my answer. Going back to what Mr. Thews says, he said about grinding. Well, don't penetrate past that throat thickness. So for analysis sake, we assume the geometry of the weld to look like a right triangle. And I like this image because it talks about a lot of things such as penetration. Like one of the things we also want to ensure is that the weld penetrates into the plate, because we're not gluing a piece of steel to another piece of steel. We're actually, when you weld, you're creating a molten pool. There's 3 melted parts. There's part A, part B, and the electrode. And so you're melting all of that into one big old pool, and then when it solidifies, it's all one part, okay? So in order to have a quality weld, that weld has to penetrate the plates a fair amount so that you have a strong joint. That's what we mean by penetration. And then there's what's called the heat affected zone, which is a little bit past that, but I'm not getting too far into weld land. I just want to make sure that you get sort of the idea. Now, one of the dimensions that we kind of need to focus on is this dimension called the effective throat. So looking down here, if I have a fillet weld that's, let's say, A, you know, the size is A, so it's like a 1/4 inch fillet weld or a 5/16 inch fillet weld or what have you, the effective throat is the distance from the root of the weld to the face of the weld. So we're talking about this dimension right here, that root to the face. That is the dimension. That's one of the most important dimensions in terms of assessing the weld's capacity, is that dimension called the effective throat. Now this is a 45, 45, 90 triangle, okay? So if it's a 45, 45, 90, you can determine the effective throat by taking A and multiplying it by the cosine of 45 degrees, or the sine of 45 degrees. And the cosine of 45 degrees is 1 over the square root of 2, and 1 over the square root of 2 is about like 0.707. So we're gonna see this term 0.707 show up here in a bit, and 0.707 is just the distance from the root to the face as a function of the weld size. Does that make sense? Okay. All right. Now, let's talk about the capacity of a welded joint. Now, I want to preface this, and all I can do is apologize. We're going to be hopping around the manual back and forth a little bit today, so that's going to happen. Fortunately, we are going to restrict ourselves to Chapter J of the spec. So if you turn to Chapter J, specifically Chapter J2, the section on welds. Did I vanish there for a second? Okay, I don't know what happened. My screen went blank over here. I don't know what happened. Okay, but I'm here. I'm here. I want everybody to turn to page 16.1-122. All right. As you're turning to that, one of the things that you will find when you're going through specs is that you tend to hop around. Like you'll read one section and it'll say, okay, this value is found in this table, and this table will point you to that table. And it's just sort of a fact of life when you're dealing with engineering specifications. It's just sort of the way it is. You know, the engineering specifications are laid out in a certain fashion, and if you're trying to design a given part, you might have to hop around to various parts of the specification to get what you need. And so that's just the name of the game. So I apologize for that. But in order to determine the capacity of a welded joint, we're going to look at two things, either the weld metal or the base metal. And it's very akin to what we did for bolted connections. Remember when we did bolted connections, we said we're either looking at the capacity of the bolt or the capacity of the plate. Well, here we're looking at the capacity of either the weld metal or the capacity of the base metal. Now, for the capacity, ultimately what we're doing is, you know, the formulas are very straightforward. You're taking a nominal stress, multiplying it by some area. You know, a stress times an area will give you an applied load. And, you know, you're going to take that and multiply it by a resistance factor. And, you know, you need to define, well, what's your area, what's your stress, and all of that. So we got to talk about what those are. And so first thing we want to do is we want to look at this part right here. Okay, so this part says the values of phi, of the base metal capacity, the weld metal capacity, all this is found in table J25. So if you look over here on the next page, 16.1-123, there's this table J25, and it says available strength of welded joints, and it's a big old table. In fact, it's so big it goes on to the next page. If you turn the page, you should see something that looks like this. This is on 16.1-124, and you should see this. It should say, let me see. Here we go. So it should say fillet welds, including fillets in holes and slots and skewed T-joints. And if you look, there's a series of rows which identify the welds that you're looking at. So there's plug and slot welds, there's complete joint penetration groove welds, there's partial joint penetration groove welds, and so on and so forth. And what we're looking at is fillet welds. All right. So is there anybody that is having a hard time finding this? Okay. All right. So if you look at this table, first off, we're splitting up into shear and tension. Now, we're going to talk a little bit about shear and tension later, but we're always going to assume welds are loaded in shear. There is a reason why, and we will get to that here in a bit. But for now, just trust me on that we're always going to assume welds are loaded in shear. So let's take a look at what's going on here. So we're going to look at the weld metal first and then look at the base metal. So with the weld metal, we've got phi. Phi is told to us, phi is 0.75. We're given a stress and we're given an area. So let's take the stress first. So what's going on with the stress? It says that the limiting stress is 0.06 times FEXX. What the heck is going on with FEXX? Well, FEXX is what's called the electrode strength. So I'm going to, if you pull up my webcam on the bottom, I want to show you something. So, come on. Lose my mouse pointer here. Okay, so if you're looking at my webcam here, I have a box of Lincoln Electric electrodes, and I want to show you something right here. So if you look here on the top, you'll see this right here, this number, this E6013. Does everybody see that? Okay, this is the electrode classification. Okay, and so those numbers mean something. Like the 1 tells you what welding position. So this number 1 means that it works for all positions. If it said a 2, that means you could only use it for flat or horizontal welds. If it said 3, you could only use it for flat welds. The 3 talks about special characteristics for the weld, and et cetera, et cetera. But the key numbers that for structural engineers that we're interested in are the first 2. So this, to me, as a structural engineer, all I care about is that this is an E60 electrode. And what does that mean? The electrode strength is 60 KSI. So if it was an E70 electrode, the electrode strength would be 70 KSI. If it's an E110, it'd be 110 KSI or what have you. So the electrode strength comes from the electrode classification itself, depending upon what electrodes you're using. So that's where that comes from. So we have a phi of 0.75. We have the electrode strength, which is 0.6 times FEXX. And what's that 0.6 popping up again? We're talking about welds and shear. Why is that 0.6 popping up again? It's because we assume the effective throat resists the load in shear. 0.6, von Mises yield criterion. I told you, anytime there was a shear, there's a 0.6 in there somewhere. And finally, the area. And the area says see section J2.2. I made your life a little easier on that one. Section J2.2a states the following. It's about material classification. It's about material classification. The material, the elements that go into it. They could get more expensive, I can tell you that. But like this particular electrode, for instance, is very applicable for sheet metal. So if we were doing like structural application, like they'd be bigger, you know. So this one's meant for like somewhat tiny jobs. So the effective area of a fillet weld shall be the length of the weld multiplied by the effective throat. Okay. So just to summarize, how do you compute the capacity of a fillet weld? Well, let's see. Phi is 0.75. The stress is 0.6 times the electrode strength. And the area is the length of the weld times 0.707A multiply that all together, boom. That's the capacity of a fillet weld. It's that simple. So all you need is the size of the weld, you need how long it is, and you need what the electrode strength is. Plug and chug. It's that simple. It's really not that hard. So just to show you some math in the future, so this is an example that we might look at on Friday. So how would you analyze this welded connection? Well, you have a 5/16 inch fillet weld that's 15 inches long, but there's two of them. So the weld length is 30 inches, the weld size is 5/16, and the electrode strength is 70 KSI because they're E70 electrodes. Go here, FEXX is 70, A is 5/16, L is 30, plug and chug. It's that simple, you know. Weld strength is easy. Now that's for the weld metal. What about the base metal? The base metal, it just says governed by J4. So you have to turn to, again, another section of the spec. Again, I apologize for that. That just, you know, you have a tendency to hop around. And so if you go to section J4, this is on 16.1-137. I made sure anytime there's something in the spec that I put a page number here so you can find it. Section J4 is concerned with connected elements. And so we're going to be focused on strength of elements in shear. Okay. If you go to section J4.3, J4.3 is about block shear. We've seen that before. So we're in section J4.2, which is just looking at strength of elements that are subjected to shear. And it's either 0.6 FY AGV or 0.6 FU ANV, whether or not you're looking at shear yielding or shear rupture. And the nice thing about fillet welds is you're not removing any material from the base metal. So the gross area equals the net area. So it's actually pretty easy. You can actually summarize all of the formulas for welds right here. It's pretty simple. For weld metal capacity, all you need is the electrode strength, the weld length, and the weld size. For the base metal, you need gross area and net area, but they're equal because for fillet welds, you're not removing any material. And the only thing that's different is that the phi value changes. For shear yielding, it's 1, and for shear rupture, it's 0.75. That's it. Like, that's all that there is to compute weld capacity. Are there any super quick questions before we call it? Well, you're getting one Friday. I'm a nice guy, aren't I? But in all seriousness, like we haven't done any problems yet, so I didn't want to load you down with homeworks based on, we haven't done anything in class. One thing I will mention, just to sort of close out what we're talking about, regardless of weld orientation, we always assume that the loads are transferred in the effective throat through shear. So you can get different stresses in the welds based on the weld orientation. So like the welds on the left would be longitudinal welds. The welds in the middle would be a transverse weld. They're going to resist the load a little differently. And we'll touch on this a little bit more on Friday. But what you see when you load welds, you know, at different angles is that longitudinal welds have lower capacity, but they have much more ductility. So you never use a transverse weld by itself. And I'll probably highlight that again on Friday. Like, we never solely use transverse weld. If I ever found out that you designed a connection with just a transverse weld in the field, I'd ask you to stick your hand out so I could do that. Because no, you don't do that. But we'll talk about that more on Friday, and then we'll get into an example. There's some other things we need to talk about with welds, because there's also weld limits as to how small your weld has to be, how big it can be, and there are different reasons for that, just as with bolted connections. Remember, if bolts got too close together, we can't tighten them, and if they get too far apart, you get water in between, where there are different but somewhat similar reasons why welds can't get too small or too big, and we have to talk about that. But we'll talk about that on Friday. I don't want to information overload you. Any quick questions? All right, I'm going to go ahead and stop the recording on Friday. We're going to continue our discussion of welds and get into some examples. That's all I got, everybody. I will see you all on Friday.